Good evening, everybody. Is my voice loud and clear? Right now? Okay. So today we are on day 2, week number 2. Day 2, week number 2. So technically we have done now this for 5 days. Is it clear? We have done this for 5 days. So we'll, without wasting more time, we'll just get into it. Have a look. Right. Look at the question carefully. Look at the question carefully. Right. 10 grams of steam, 10 grams of steam, 10 grams of steam at 100 degrees Celsius. So steam here is mixed with 10 grams of ice. Now, all that you need to know is, you need to know that latent heat of vaporization is greater than latent heat of fusion. There. Latent heat of vaporization is greater than latent heat of fusion. So vaporization, normally it's about 210 to the power 6 joules per kilogram. Right? Latent heat of fusion is about 310 to the power 5 joules per kilogram. So 10 grams of steam will give a lot of energy, and you can obviously see that ice will completely melt and the temperature will increase. Now they don't expect you to do the calculation, but if they ask you the exact value for this, there will be a mix of ice and steam at 100 degrees Celsius. So guaranteed, it's going to be greater than 50 degrees Celsius. So that's what they want. They want to check whether you understand that latent heat of vaporization is more than latent heat of fusion. So 10 grams of steam will give more energy than 10 grams of ice. So the energy given by steam will completely melt the ice and bring it to a higher temperature. In reality, there will be a mixture of water and steam at 100 degrees Celsius. Let's write that down. Here, the main focus of the question, is to consider that the latent heat of vaporization is greater than the latent heat of fusion. Is greater than the latent heat of fusion. Is greater than the latent heat of fusion. Therefore, the energy given by 10 grams of steam, will be much more larger than 10 grams of ice. Finally, there will be a mixture of steam and water at 100 degrees Celsius. Which is greater than 50 degrees. Which means it is greater than 50 degrees. So here, answer number 5. Right. Look at this carefully now. An ideal gas of volume 300 cubic centimeter at pressure 1 atmosphere and temperature 27 degrees Celsius is compressed to 5 atmospheres and then heated to 127 degrees Celsius at constant pressure. So you can see pressure remains same. The new volume of the gas will be careful now. Huh? So if you look at this carefully, if you take the pressure volume graph, just to give a small idea, so an ideal gas at 1 atmospheric pressure, temperature 27 degrees Celsius, volume 300 cubic centimeter, is compressed at constant pressure. They have said compressed to 5 atmosphere. So this part you have to remove. Compressed to 5 atmosphere. So here we are compressing it. Compressing it to 5 atmospheres. We don't know how, but somehow 5 atmosphere. There you will get a different volume. There you get a different volume. And then heated to 127 degrees Celsius. Heated to 127 degrees Celsius. So we don't know. Heating means constant pressure, volume will increase. Heating to 127 degrees Celsius at constant pressure. The new volume of the gas. What's the new volume of the gas? So if you look at this, their job is they are asking you this. So this location here, and this location here, we can directly apply gas laws. What is it? P1 V1 over T1 equals P2 V2 over T2. Okay, no? So what's the pressure here? 1 atmosphere, volume 300 cubic centimeters, temperature is 300 Kelvin. Pressure there is 5 atmospheres, volume we don't know, temperature is 127, that means 400 Kelvin. 300 cancel off, V2 is equal to 400 divided by 5, 80 cubic centimeters. 80 cubic centimeters. Correct answer is answer number 3. Correct answer is answer number 3. So we don't know whether it's a straight line variation. I just do it. We don't really care. We just think about these two locations. Think about these two locations. Apply what? Ideal gas or combined gas equation. Combined gas equation. Remember, you must remember that this is going to be a closed system. Closed system. Nothing is coming in, neither nothing is going out. Okay. Nothing is coming in or going out. Right. Next question. See the question carefully. A uniform glass means same cross-sectional area. So here, if I push this down a bit, here you go, right? Here, cross-sectional area, we'll take it as A value. Cross-sectional area, right? Okay. The length of the glass tube is 2 meters with one end sealed containing air. One end sealed containing air. Right. It is pressed vertically. It is pressed vertically down into mercury bar until the mercury rises halfway up in the glass tube. If the atmospheric pressure is 76 millimeter mercury, then the depth H would be, right? So before you do anything, first consider when the tube is completely outward. 2 meter long tube. What is the air inside? Air inside is at atmospheric pressure. Air inside is at atmospheric pressure. Now, if you look at this carefully, here you have atmospheric pressure. Here you have atmospheric pressure. Here and here. What can you say about the pressures? Pressures are equal. Pressures are equal. Inside this, we have gas pressure, let's say P2. Here, gas pressure is P1. Here, gas pressure is P1. Simplify this. Pressure at A equals pressure at B. Pressure at A equals pressure at B. Pressure at A is equal to atmospheric pressure plus H rho G. Don't put density, we'll do in centimeter mercury. Inside the tube, P2 plus 1 meter is 100 centimeter. Atmospheric pressure is 76 centimeter mercury. P2 plus 100. So you can simplify the relationship here. P2 equals H 76 minus 100. 76 minus 100 is minus 24. Minus 24. What about the volume of gas here? Volume of gas here. The volume of gas is going to be volume of gas. Area into from here to here height is 1 meter. 1 meter is 100. Right. What can you consider here? Pressure there is atmospheric pressure. Atmospheric pressure is going to be 76 centimeter mercury. And what can you say about the volume? Volume is A times 2 meter. So when I'm sinking it inside, will the temperature change? No, temperature will not change. So I can apply P1 V1 equals P2 V2. So apply for P1 middle 76 A times 2 meters. 2 meters is 200 centimeters. Pressure P2 is H minus 24 multiplied by A times 100. Carefully look. Carefully look. Area cancel off. 100 times 1, 100 times 2. Simplify. 152 is H minus 24. Take 24 to the other side. H is equal to 152 plus 24. 176 centimeters. 176 centimeters means correct answer is answer number 4. Correct answer is answer number 4. Right now? Carefully write it down. Carefully write it down. Now, this case you have to consider. Before you submerge, what was the situation? Before you submerge, everything was atmospheric pressure and the length here was 2 meters. That's all. Right now? Okay. At what temperature is the RMS speed of hydrogen equal to hydrogen molecules at 27 degrees Celsius? So here, root mean squared speed, no? RMS speed. Root mean squared is 3RT over molar mass square root. 3RT over molar mass square root. Okay, no? Square root value there. 3RT over molar mass. Right. Now look at this carefully. Look at this carefully. Now how will you simplify this? How will you simplify this? So root mean squared velocity of nitrogen equals root mean squared velocity of hydrogen. Root mean squared velocity of hydrogen. So if you substitute there 3R, temperature we don't know. Nitrogen molecules is 14 times massive than hydrogen molecules. Right. You can put K as well, molecular mass or molar mass, same way. Here 3R, temperature 300 Kelvin. Here mass of hydrogen. Square root values cancel off. Here you go. 3R M2, 3R M2 cancel off. Square both sides. T over 14, 300. T is equal to 0, 0, 5200 Kelvin. So 5200 Kelvin means how much of Celsius? 5200 minus 273. How much? 7294. 4927 Celsius. See whether you have the answer. 4927 Celsius. There you go. 4927 Celsius. Right. What's the answer? Sorry. 4200. No, I'm sorry. 4200. 4200 minus 273, 3927. 3927. 3927 is not there. 3927 is not there. That means this question, I think, if I check the scheme, yes, this question they had given all. This question they had given all. So this is 4200, 4200 here, 4200, 4200, 4200 minus 273, 3900. 3900, 3900 and 27. So that answer is not there. So be careful. That answer is not there. So all. Okay. That answer is not there. All. Right. Question number 5. Question number 5. Look at this carefully. If a water molecule is placed in an electric field as shown in the figure, which orientation is most suitable? Which orientation is most suitable? Now look at this. These are positive charges. These are negative charges. Very basic. Positive charges, negative charges. Right. Now, if I mark the water molecule, negative charge should be closer to the positive, while the positive charges, hydrogen molecules, should be towards the negative. Okay, no? Then only it will be in stable equilibrium. Stable equilibrium. Right? Stable equilibrium. Okay, no? So if it's here, far away means uniform electric field, uniform electric field. Here, heavier molecule is down, heavier molecule is down. That is attracted towards the positive plate. Oxygen there is negatively charged. So 2 minus 1 or 2 minus 2 like that. Or you can put 2 minus signs there. You can put 2 minus signs there. There you go. This is how it will be in stable equilibrium. This is how it will be in stable equilibrium. Okay, no? Let's write this down. Have a look. The oxygen molecule will be closer to the positive plate. The oxygen molecule will be closer to the positive plate. I hope you drew this. And the hydrogen molecules will be closer to the negative plate. And the hydrogen molecules will be closer to the negative plate. And in this system, it is in stable equilibrium. In this system, it is in stable equilibrium. In this system, it is in stable equilibrium. Because even if there is a moment, stable equilibrium will take place. Even if there is a moment, stable equilibrium will take place. Even if there is a moment, stable equilibrium will take place. Right now? Okay. Look at this carefully. A point charge plus Q is placed at the center. Point charge plus Q is kept at the center. There you go. Another point charge plus Q is carried separately from A to B, A to C, A to D. Work done in carrying the charge. Right. What is the potential at A? Potential at A is Q divided by 4 pi epsilon naught radius R. So potential at A, potential at B, potential at C, potential at D, all are same. Potential at B, potential at C, potential at D, all are same. So what can you say here? You can say that is an equipotential surface. A, B, C, D are on an equipotential surface. Equipotential surface. Therefore, work done will be zero. No work done. So zero work along all the paths. Correct answer is answer number 6. Correct answer is answer number 6. Okay. Right, no? That is small sentence. A, B, C, D are on the surfaces of a sphere. A, B, C, D is on the surface of a sphere. Therefore, the potentials will be the same. Therefore, the potentials will be the same. Therefore, the potentials will be the same. Right. Okay, no? Okay. Moving up. Look at the word carefully. Look at the word carefully. A horizontal conducting wire x 20 centimeters has a mass 4.5 kilograms. So 4.5 gram means 4.5 grams convert to kilograms into Newton. Is in Newton. Na? G means acceleration due to gravity. A magnetic field of 0.15 Tesla. Magnetic field of 0.15 Tesla is directed into the paper. Remember, this cross mark means field lines are into the paper. Field lines are into the paper. What magnitude and direction of the current in the wire XY is required to nullify the tension in the wire? What do you mean by nullify? Now, who is holding this wire? The weight is balanced by the tension. How can I make the tension zero? I can make the tension zero if another force can balance this. What is that other force? Magnetic force. The magnetic force acting upwards, if it is equal to this, tension there will be zero. How can I find it? Fleming's left hand rule. So if you take the left hand, thumb, first finger, second finger of the left hand. The thumb here will give, thumb here will give, thumb here will give the direction of the force. First finger will give you direction of field. First finger will give you direction of field. Second finger will give you direction of what? Current. Second finger will give you direction of current. Now look at this. Now what are they asking you? They are asking you, how can the tensions be zero? So tensions are zero if the weight is balanced by another force, magnetic force. So magnetic force should balance the weight. 4.5, 10 to the power minus 3 G. Look at the board now. Magnetic force is BIL, B-I-L. 4.5, 10 to the power minus 3 G is 10. What is your magnetic field? Look at the finger now, left hand rule. Feel into the paper. Current along the board, force upwards. Feel, force upwards. Feel we know, force we know. So current is X to Y. Current will be X to Y current. Right. So magnetic field is 0.15. Current we don't know. Length is 20 centimeter, 0.2 meters. 4.5, 10 to the power minus 2. Right. Simplify this carefully. If you simplify it, I is equal to 4.5 divided by 33 decimal places, 0.03 times 10 to the power minus 2. Jump 2 decimal places, 450 divided by 350, 10 to the power minus 2. 1.5, 10 to the power, 1.5 amperes. 1.5 amperes. 1.5 amperes, what's the direction? X to Y. 1.5 amperes direction X to Y. There you go. Right there. The tension can be zero only when the tension can be zero only when the weight is completely balanced by another force. The weight is completely balanced by another force. By using Fleming's left-hand rule, we can show that the upward magnetic force can balance the weight. The upward magnetic force can balance the weight. The upward magnetic force can balance the weight. Upward magnetic force can balance the weight. Okay, no? Right. Sending this up. Okay. Next question. The Wheatstone bridge shown in the diagram is balanced. Now, what do you mean by balance? P divided by Q should be equal to R divided by S. Right. So, its balance means the potential difference here. VA equals VB. The potential difference, which is VA minus VB, will be 0. No current will pass through. Galvanometer reading is going to be how much? 0. Right. The balance condition does not change when the galvanometer G is replaced by another one with a different resistance. Whatever resistance you put is useless. Why? Potential at A and potential at B is same. So does not change. A is correct. A is correct. B. The cell E is replaced by another one with a different EMF. Cell E is balanced by another one with a different EMF. So whatever the battery, what's important is the ratio. What's the ratio? P divided by Q is equal to R divided by S. So P divided by Q, ROS won't change. No? So whatever the battery, balance won't change. But if they ask you whether the potential values will change, yes. But this value and this value are equal. Right. The resistance R and S are interchanged. Now, if you interchange this, then you have a problem. Then this ratio is not satisfied. So this is wrong. A and B only will be correct. Right there. When the Wheatstone bridge is satisfied, you can mark this. The potentials at point A and point B will be the same. The potentials at point A and point B will be the same. Potentials at point A and point B will be the same. This means no current will pass through the galvanometer. No current will pass through the galvanometer. No current will pass through the galvanometer. Even if you replace it with a different galvanometer, or use a different cell, the potential at A and B will remain the same. The potential at A and B will remain the same. Right now, potentials at A and B will remain the same. So these call your Wheatstone bridge, huh? Wheatstone bridge condition. Wheatstone bridge condition. Right now? Okay. Right. Wait. An immersion heater which is connected to home electric supply having a resistance of 150 ohm at the operating temperature is immersed in boiling water. The specific latent heat of vaporization is given. Rate of production of steam, right? Q is equal to mLV. Rate of supply of heat means, if I look at this carefully, Q divided by T, here also divided by T. What is Q divided by T? Power. How do you find the power? Voltage is given, resistance is given. So here V squared divided by R is the power. M over T, LV. So these are basic O-level science. Power given by a heater, voltage and resistance given. Power is equal to V squared over R. So now you can substitute. What is M over T? M over T, make it the subject, rate. Voltage V squared divided by resistance divided by LV. 230 into 230 divided by resistance 115. LV is going to be 2.3 10 to the power 6. 115 times 1, 15 times 2. Jump a decimal place. 23 times 100. 23 times 100 here. So what's your answer? Mass flow rate is 2 10 to the power minus 4 kilogram per second. 2 10 to the power minus 4 kilogram per second. Correct answer is answer number 2. Correct answer is answer number 2. Right. Once you need it, write it down. Very basic. Actually, O-level work. Right. 100-watt filament bulb is replaced by an energy saving bulb of 10 watt. If the bulb is used for 4 hours daily, the electrical unit saved in 100 days. Right. 100-watt means I can write in kilowatt, 0.1 kilowatt. Electrical consumption. Electrical consumption 0.1 kilowatt 4 hours, 0.4 kilowatt hours. How many days? 100 days. Simplify it. If you simplify this, 40 kilowatt hours. 40 kilowatt hours is 40 units. Now I'm using 10 watt, 0.01 kilowatt. Energy consumption 0.01 for 4 hours a day, 100 days. You will get 4 kilowatt hours. What is your saving? Electrical consumption saving. Electrical consumption saving. Subtract, you will get what? 36 kilowatt hours. 36 kilowatt hours. 10th one, answer number 3. 10th one, answer number 3. I think this is in your O-level now. These are O-level work. Here kilowatt hour is kilowatt multiplied by time. Power into time is energy. So kilowatt hour is unit of energy. Okay. Kilowatt hour is unit of energy. Right. In the circuit shown, F becomes 1N. Now these are OR gate. These are AND gate. These are also AND gate. OR gate, AND gate, AND gate. Right. So here, if you write this in Boolean notation, A or B, A and C. Here AND means A or B and A and C. This is your final output. Right. This is your final output. So here if you look at it, A0, B1, C1, look at the board. 01 OR gate is 1. 01 OR gate is 1. 01 AND gate is 0. 10 AND gate is 0. The first one is wrong. Second one. A0, B0, C1. 0 is 0. 01 is 0. 0 is 0. If somewhere here it's 0, it's finished. Even this one. 1, 0, C is 1. 10 is 1. Here 0. Guaranteed 0. These also finished. So technically, what should be your answer? C can't be 0. C can't be 0. C can't be 0. Huh? And AND gate, no. A is 1. B is 0. C is 0. Interesting. Here it's 1. 10 is 0. Oh, wait. Here A and C, no? Here 1-1 situation is there. A1, C1. A1, C1 situation is there. So A1 situation, third case, 1. So this one, A1, C1. So here if you look at it, A1, C1 situation. A1, C1 situation. A1, C1 situation. Right. Look at this. Anyway, if A is 0, you have a problem. If A is 0 means C is 0, here 0, here 0 means there 0. So your option should be basically A can't be 0, B may be 0, C can't be 0. A and C can't be 0 means I think B is the third answer. Let's see. A is 1, B is 0, C is 1. 1 0 is 1, 1 1 is 1, 1 1 means 1. Yes. Correct answer is answer number 3. Correct answer is answer number 3. Right? So here this is connected to A, A and C. Right. Question number 12. Figure shows black body radiation curve. Now in a black body radiation curve, what's your characteristic? Here at a particular maximum or particular lambda, intensity will be maximum. Intensity will be maximum. And when temperature increases, I'll show you here, temperature increases, the peak also gradually increases. So if I look at these temperatures, T1, T2, this one is T3, this one is T4. T1 smaller than T2, smaller than T3, smaller than T4. The location where the maximum wavelength occurs will slowly go to the left. There, right. What are they asking? At higher temperatures, lambda m will be lower. Correct. Intensity would be higher. Correct. Velocity emitted by the radiation would be higher. Wrong. All are electromagnetic. All are electromagnetic. Remember, radiation is infrared region. Whatever happens, even electromagnetic. Electromagnetic means travels at the speed of light. So your correct answers are A and B are true. A and B are true. Yes. 12th answer, A and B are true. Let's write it down. In black body radiation, in black body radiation, when the temperature increases, the wavelength maximum intensity is emitted. The wavelength where maximum intensity is emitted. The wavelength where maximum intensity is emitted gradually moves towards the left. Gradually moves towards the left. Can you see? Gradually moves towards the left. This means when the temperature increases, the wavelength where maximum radiation is emitted will reduce. The wavelength maximum radiation is emitted will reduce. The wavelength where maximum radiation is emitted will reduce. Okay, no? And all radiations emitted will be electromagnetic. All radiations emitted will be electromagnetic. Will be electromagnetic. Right. Okay, no? Now look. A monochromatic beam of light is falling on a photosensitive surface. Can you remember yesterday? Photoelectric effect. Yesterday, I think they asked, what is photoelectric effect? It represents what? The particle nature of light. An increase in intensity, what will happen? When intensity increases, intensity is proportional to number of photoelectrons emitted. Photoelectrons emitted. That means one photon will emit one electron. When the intensity increases, number of photons will increase. Number of photons increase means number of photoelectrons will also increase. One photon, one electron will emit. Okay, don't forget. So when you increase the intensity, remember incident frequency should be greater than threshold. This condition must be satisfied. Then what happens is intensity increases, photo emission will also increase. Correct one is answer number 1. Will increase the rate in which photoelectrons are emitted. Photoelectrons are emitted. That's right. The intensity of light is representing the number of photons in the beam of light. Representing the number of photons in the beam of light. When the intensity increases, number of photoelectrons will increase. When the intensity increases, number of photoelectrons will increase. Number of photoelectrons will increase. So the photo current will increase. Right. Nice question. Surface tension 1. Two bubbles core is, once they are joined together, the radii of the two bubbles become A and B. The radius of the curvature, like this. Right now, I'll redraw that a bit. I think I'll go to the board and draw this for you all. Look. So this is one. So this is what you mean by interface. Right. Here they are given you radius of A is larger than radius of B. Right. Radius of A is larger than radius of B. So radius of A is larger than radius of B. Remember, this interface will have a different radius. Right. Now look. So what's the rule? Soap bubble. Excess pressure is equal to 40 divided by radius of the bubble. Excess pressure is 40 divided by radius of the bubble. Look at the board. Two soap bubbles. When there is a soap bubble, then the excess pressure will double. So 40 over R. A is larger than B. What's the radius of curvature between the bubbles? What's the radius of curvature with the bubbles? Right. Now, smaller the radius, bigger the pressure. So here pressure is P1. Larger the radius, smaller the pressure difference. So here pressure is smaller. Outside you have atmospheric pressure. Here also outside you have atmospheric pressure. So if I apply for the small bubble, small bubble here, this is bent this way. That means pressure P1 is more. Why does a flat surface like this bend this way? Because the push from here is large. The flat surface will bend if the push is large. P1 minus PATM, that is equal to 40 over simple B. What about the large bubble? Excess pressure here. P2 minus PATM, 40 over simple A. Look at the board. What can you say about this interface here? What can you say about that interface? I'll color it. There you go. Different radius. That is, which pressure is large? This pressure is large. P1 minus for the interface. P1 minus P2, 40 over R. 40 over R. Right? Have a look. Now, what is P1 minus P2? Equation 1 minus equation 2. 1 minus 2. PATM cancel off. P1 minus P2. 40 over B minus 40 over A. What is P1 minus P2? 40 over capital R. 1 over B minus 1 over A. Don't forget, here also 40, here also 40. 40, 40, 40 cancel off. 1 over R is 1 over B minus 1 over A. So what have I applied? I have applied excess pressure difference. This is called excess pressure equation. This is called excess pressure equation. P1 minus PATM 40 over B. P2 minus PATM 40 over A. If I subtract this from this, P1 minus P2 will come. P1 minus P2 will come. Also for the common interface, I can write P1 minus P2 is 40 over capital R. These two are equal means these two are equal. Equate, you get the relationship. Once you need it, quickly write it down. Or at least take a photo. Quickly work. Right now. So now you can simplify this. You can simplify this. I will finish it here, otherwise in vain. 1 over R is equal to 1 over AB, A minus B. Turn upside down, AB divided by A minus B. That's your answer. That's your answer. Okay. So do you have the answer? Have no? Answer number 4. Answer number 4. 14th answer number 4. 14th answer number 4. Right now? Again, for the ones who want to look at it, have a look. So you can clearly see the application. Huh? You can clearly see the application. Right now? Okay. Let's move on. Right, nice question. Read below. Wait. The material of a wire has a higher value of Young's modulus than the material of wire B. Right. So material X has higher Young's modulus than material Y. Higher Young's modulus than material Y. Right. The two wires are subjected to the same tension, same force. The extension of wire X is found to be more than that of Y. More than that of Y. Right. Let's look at this carefully. Young's modulus is stress divided by strain. So here Young's modulus equation, force divided by area over extension over initial length. Extension over initial length. Young's modulus equal F over A, X, L goes on top. Right. What are they saying? Young's modulus of X is greater than Young's modulus of Y. If Young's modulus is larger, here same force, length of X, we don't know the length of X, divided by area of X. Extension of X. Here force, length of Y, area of Y, extension of Y. Right. Have a look. Same force cancel off. Same force cancel off. What are they saying? Extension of X is found to be more than that of Y. X is larger than Y. Look at the board now. It is very important. So these what they are given, you know. These what they are given. Right. So extension of X is larger than extension of Y. Areas are different, lengths are different, we don't know. Right. The above will happen only if the diameter of X is smaller than that of Y or Y. Be careful. No? So they are telling you Young's modulus is also larger. Since our condition is this, what I'll do is I will erase this and then carefully put the condition. Look at the board. First one, extension of X is greater than extension of Y. Please make extension the subject. If you make extension the subject, force, length of X, area of X, Young's modulus of X, force, length of Y, area of Y, extension of Y. Look at the board now. From this you can cancel off certain things. Force is cancelled off. How can extension be larger? Now looking at this ratio, carefully look and tell me now. They are also telling you EX is larger. EX is larger means this ratio should be small. No? Denominator is large. EX is large. EX is large means what can you say? LX over AX. Numerator should be absolutely large. Numerator should be absolutely large. Or area here should be very, very small. For this to be larger. So if it is large, this becomes small. If EX is large, this value will become small. If EX is large, think if EX is large, bottom one is large, the ratio will become small. How can this ratio be larger? Larger, two things. The diameter here is very, very small, or the length here is very, very large. Right. The above will happen only if the diameter is smaller than that of wire. Only the diameter becoming smaller, is it enough? No. Length also comes into play. Length also comes into play. So be careful here. Sometimes you might think directly this is correct. But you must be careful. So here, if you look at it, EX is large, the ratio will become small. How can the ratio be larger? LX should be larger, area should be smaller. So here diameter is small. Just the diameter smaller won't help. Length also should change. Statement A is wrong. Right there, Will? It's clear, no? It's clear, no? Have a look. Length of X over area of X EX greater length of Y AY EY. This is your condition. You can't change that. So for this condition to be satisfied, if EX is large, they have given you EX is large. This is also given. If denominator is large, the ratio here will be small. How can this be larger? LX over LX. So therefore, I'm telling you, LX over AX, that is going to be very much more greater than LY over AY. This ratio is large. So here they have only talked about diameter. Diameter is not enough. Diameter should be small, length should be large. Statement A is wrong. So A is wrong means 1 is wrong, 4 is wrong. There you go. Method of elimination. Right there, right there, right there. Extension of X is larger than extension of Y. Extension of X is larger than extension of Y. And Young's modulus of X is larger than Young's modulus of Y. Young's modulus of X is larger than Young's modulus of Y. This means for this ratio to be satisfied, this means for this ratio to be satisfied, this means for this ratio to be satisfied, the diameter of X will be very small. The diameter of X will be very small. Diameter of X will be very small, and the length of X will be very large. Diameter of X will be very small, and length of X will be very large. Is it clear? Perfect. Understood? No? So looking at this inequality, EX is large means ratio will drop. Can this be bigger? If LX over AX is bigger than LY over AY. How can this be bigger? LX is very much larger and diameter is of X is much more small. Okay, no? Right. Statement B. The above will happen only if the ratio original length over diameter. Original length over diameter for X is higher than Y. Original length over diameter, diameter is wrong, diameter squared. Statement B is also wrong. So original length over pi r squared, no, pi d squared, no, diameter squared. That is okay. That for X is larger than L over D squared for Y. Diameter, correct? Diameter is proportional to area, right? So it should be diameter squared. They have only given diameter, so B is also wrong. So B is also wrong means this is also wrong, this is also wrong. Right. Okay, no? Clear, no? So length over area should of X should be larger. Length over area means length over diameter squared, not diameter, diameter squared. Okay, right. The above will never happen. The above will never happen if the length of the wire X is shorter. Length X is shorter, that means Lx is shorter, Lx is less. That means area, diameter here should be very, very small. These also wrong. Right there. Statement A is wrong. Sorry, we wrote that. Statement B is wrong. Statement B is wrong. Because length over area of X or length over diameter squared of X. Length over diameter squared of X should be greater. Should be greater. Should be greater. Okay, no? Analysis is okay? Right. Statement 3 is wrong. Statement 3 is wrong. Even though the length of X will be small. Even though the length of X will be small. If the diameter of X is very small compared to Y. If the diameter of X is very small compared to Y. So that the length area ratio is larger. So that the length area ratio is larger. So that the length area ratio is larger. Then this condition is satisfied. Then this condition is still satisfied. So I'm sad to say that there is no answer here. Even C is wrong. So I think they gave all for this at that particular year. All is the suitable answer. All is the suitable answer. Right? Okay, now? Clear? Right. Look at the board carefully. A steel bowl floats in water with the brim facing upwards. Brim facing up. Brim facing up. If water is poured slowly, which of the following figures shows its position on the verge of sinking? You can't do this. You can't do this. Neither you can do that. Neither this. Only suitable answer is that. Can you remember? What do you remember? There is a level where you can fill water. Outside, inside, the difference here is constant. H is constant. Here, look at this carefully. Inside water level, outside water level. As long as the difference between the inside and the outside is constant, no sinking will take place. If H constant. But the moment when H reduces, sinking will occur. The correct statement is 1, right there. If the difference of the liquid, between the outer layer and the inner layer, is different and constant, no sinking will take place. No sinking will take place. No sinking will take place. But the moment simple h reduces from this constant value, sinking will take place. Sinking will take place. Okay, no? Right. Okay. Following graph shows certain quantities with displacement undergoing simple harmonic motion. So I think in the 2000 paper we made this. What is this constant? Constant means total energy. No, total energy will be constant. Total energy will be constant. So this looks like total energy. Here there is a displacement. So the displacement, d displacement. So this will be your time axis. So normally we do with y axis, x axis. No? We have interchanged the axis. That is time. This can be either force or acceleration. Either way, force or acceleration. From this we can say correct answer is answer number 2. Correct answer is answer number 2. Okay, no? Simple work. Next one. The graph representing Vt for the following. So here gradient of the graph, d acceleration, area is positive, acceleration, area is positive. So deceleration, acceleration, correct answer is answer number 1. Deceleration, acceleration, areas are added, displacement is added, answer number 1. Okay. Right. A bird of mass m sits tightly stretched on a telegraph wire. Now, actually, if you look at this, the weight of the bird is here, tension here, tension here. Don't forget this angle is very, very small. This horizontal angle is going to be very, very small. Here theta means here also theta, here also theta, take component. T cos theta is here, T cos theta is there, T sin theta, 2T sin theta is on top. So what can you say? Sum of forces in the upward direction balances sum of forces in the downward direction. Upward direction you have 2T sin theta, that is equal to what? mg. Okay, no? They're asking what is tension. Look at the board carefully and write. When theta gets smaller, sin theta will get even smaller. This is smaller means tension is greater than mg. Tension is larger than mg means more than mg, answer number 3. Right there. When the bird is sitting on the wire, the wire will sag to a very small angle. The wire will sag to a very small angle. The wire will sag to a very small angle. If we balance the vertical forces, we can show that. Tension is larger than mg. Right now. MCQ number 20. Look. Letter E is cut. Where is the center of gravity? Now you can apply ratio theorem. Can you remember? Simple. So I'll divide this into 3 parts. 1, 2, 3. Right. Here the mass is at the center. Here the mass is at the center. Here the mass is at the center. Here center. Here also center. All equal mass. So if you apply ratio theorem, look at this carefully. If I take these two, 1:1 ratio, here 2m will come. So altogether they are 3m. No? So all they are taken. Now take this one and that one. 3:1 ratio. 3:1 ratio means answer is answer C. So there you go. 40th one. Easily we can find the answer. Answer C. Right. Okay, now. Right. Look at the board now. Structured assay is connected to thermal physics. Structured assay is connected to thermal physics. Read the question carefully. I'll read it from here. Right. Here we go. You are provided with a metal studded plastic cap. Metal studded plastic cap. Metal studded plastic cap. On top, there is metal plastic cap. And asked to find the specific heat capacity of plastic. We are asked to find the specific heat capacity of plastic. Using method of mixtures, the plastic content of each nail is 30%. 30% of the mass of the nail is plastic, means 70% is metal. Right. So don't forget, 70% is metal. Right. Okay. So what are they asking? What are they asking? If the nails at 100 degrees Celsius, if the nails are at 100 degrees Celsius, a calorimeter and water are provided, what other apparatus would you require to carry out this experiment? Assume that the plastic can be heated to 100 degrees Celsius without affecting the properties. Without affecting the properties. Right. So here calorimeter is given, water is given, but other apparatus do you need? Well, to measure the mass, you need a scale and you need a thermometer. So here you need a thermometer, and then of course you need a scale. You need a scale. Now this can be any scale, triple beam balance, 4 beam balance, or even a digital scale. Either way. So I will select actually digital scale. Accurate, it will give readings of digital scale. Right. Right. Digital scale. Look at this carefully. Right. Okay, now moving forward. Write down a list of measurements that you will take in the experiment. Make sure you write them in order. Interesting. Mass of empty calorimeter and stirrer. M1. So what do you do then? You fill water. Mass of calorimeter, stirrer, and water. What else? Then you insert the metal. Then you mix. Or before you insert, you have to find initial temperature. Initial temperature of water in the calorimeter. Initial temperature of water in the calorimeter. Okay, no? Initial temperature of water in the calorimeter. Then I'm mixing the 100 degrees Celsius metal and stir, temperature will increase. Final maximum temperature of the mixture. Now metal is also inside. Right. Then what do you do? Mass of final mass final mass of the calorimeter with all its contents. With all its contents. Okay, no? With all its contents. Right? Right. Next one. Write down an expression for CM. CP, CM, CW. Assume that the calorimeter and the metal part are made from the same metal. So heat given equals heat absorbed. Who is giving heat? Nail is giving heat, metal. M3 minus M2, out of this, 30% is plastic. Specific heat capacity of plastic, 100 minus theta 2 plus. Here M3 minus M2, these for the metal, 70% is metal CM, 100 minus theta 2 equals. Who is absorbing heat? Calorimeter is absorbing heat. M1 CM, theta 2 minus theta 1. Water is absorbing heat. M2 minus M1, specific heat capacity of water CW. T2 minus T1, this is your relationship. This is your relationship. See whether you wrote this carefully. Right. Okay. Right now. Okay. Right now, I'm moving up. State the experimental error that can affect the result of the experiment in addition to the errors associated with the above measurements. So apart from the measurements, what are the errors which may occur? Number one, heat loss from the nail. Heat loss from the nails. Heat loss from the calorimeter due to convection. Due to convection. Due to convection. That means before you close the lid, what happens? Convection heat loss may occur. Convection heat loss may occur. Yeah. Convection heat loss may occur. Also, you can say heat loss due to evaporation. Evaporation also may occur no? Before you close the lid. Heat loss due to evaporation. Due to evaporation. Okay, no? Right. Suggest a suitable method to minimize the heat loss to the environment. So what's the suitable method? Quickly insert the nails into the calorimeter quickly close the calorimeter lid, quickly close the calorimeter lid and continuously stir. Continuously stir. Continuously stir. Right now? Right? What is the next one? Because there is heat loss, how do you normally do cooling corrections? We can start the temperature a few degrees Celsius below room temperature. Insert the metal until the temperature is about few degrees Celsius above room temperature. Right there. We start the experiment. We start the experiment 5 degrees Celsius below room temperature. Below room temperature. And we heat it. And we mix it. And we mix the metal until it is 5 degrees Celsius above room temperature. Right. So you have to make sure that dew doesn't form. Huh? So very important here, dew should not form above dew point. No space, but I'll put in brackets here. Above dew point. Huh? It should be greater than dew point. So, okay. Would you expect to obtain a more accurate value for CP if relatively large quantities of nails and a small quantity of water was used? Obviously. Large quantity of nails, small quantity of water. What can you say? Large amount of nails will give a lot of energy. What will happen? Quick evaporation or vaporization will take place. Would you expect a more accurate value? Answer is no. Large amount of nails. Large amount of nails. Answer is no. Large amount of nails when we mix with small amount of water. With small amount of water. Small amount of water. Quick evaporation will occur. Heat distribution will be not uniform. Heat distribution will not be uniform. Heat distribution will not be uniform. Some more you can write. All the nails will not properly mix. Will not properly mix with water. This is also one reason why it will be non-uniform. Okay, no? Right. Okay. Then what are they asking? Give a valid reason as to why the value obtained for CP in this experiment is more accurate than the value that would be obtained had a large lump of plastic be used. If you use a large lump of plastic, what will happen? If you use a large lump of plastic, what will happen? heat transfer or conduction will be minimum. Only plastic heat conduction will be very slow. It will take a long time. Therefore, it will take a long time. It will take a long time to transfer the heat. To transfer the heat. Transfer the heat. Therefore, there will be more heat loss. More heat loss to the environment. Remember, if it takes a longer time, that means bigger heat loss. Bigger heat loss guaranteed will take place. Okay, no? Right, no? Right, no? So remember this, huh? Only plastic heat conduction will be very slow. It will take a long time to transfer heat. There will be more heat loss to the environment. So not suitable. Right? Okay. Right. Essay question is a optics question. Essay question is a optics question. Right. Look at the board carefully. Now this optics question, these are very basic. But look at it carefully when you do the calculation. Right. We'll use a different color. Okay. A monochromatic ray of light is falling with an angle of incidence theta along the glass block ABCD of refractive index 1.6. Consider only the rays falling on the surface AB after refraction at the surface AD. After refraction from AD falls directly on AB. Disregard theta equals 0 situation. Find the critical angle for glass. Look at the board. This is glass. This is air. If I draw, this you all can do. Huh? Denser air away from the normal goes along the boundary. This is your critical angle. If that is your critical angle, you can say 1.6 sin C, Na sin 90. 1.6 sin C, Na sin 90. Sin C is 1 over 1.6. 1 over 1.6. Now take sine inverse. C is sine inverse 1 over 1.6. C is sine inverse 1 over 1.6. Using your logbooks, get the answer. Using the logbooks, get the answer. Your answer will be 38 degrees 41 minutes plus or minus 6 minutes. In your marking scheme, plus or minus 6 minutes they will give. That means this can be either 35 minutes or 47 minutes, no problem. But 38 degrees should be there. Okay, no? Remember, this plus or minus part is given in the marking scheme, original marking scheme. This is the variation. So if you got inside this, accepted. That means 38 degrees, 35 minutes to 38 degrees, 47 minutes. Inside this range, accepted. Inside this range, accepted. Right, no? Okay. Right? Okay. Show that the ray must undergo total internal reflection at surface AB for all possible values of theta. All possible values of theta. Right. Nice question. I think I will move to the board, and in the board I will show this much more easier. Look at this carefully. Now, if you look at this, here you go. A, D, here B. A, D, B. Right. Incident light ray disregard theta equals 0. So here comes it theta. Rarer, denser towards the normal. Here R. This angle 90 minus R. Right. Look at the board carefully. Observe this, then write. Theta is greater than 0. Theta is greater than 0. Right? So very small increase. If theta is very small, how will I logically write this? Right. So very small means these also very small. Smaller. Smaller means this is going to be larger than the critical angle. So total internal reflection will take place. Right? So when theta increases, the next situation, theta increases when the angle of incidence is maximum. Here critical angle. Here 90 minus C. Let's see what happens. Right. Look at this carefully. When, let's work for this. When theta equals 90, R equals critical angle 38 degrees 41 minutes. Okay, now? Then we can say 90 minus C, this angle here, 90 minus C. 90 minus C means how much? 8960 minus 3841. 19 here, 5190. So 5119 degrees is greater than the critical angle. Therefore, total internal reflection will occur. Total internal reflection will occur. So very simple, when theta is maximum. When theta is maximum. Now logically think. When theta reduces from 90. When theta reduces from 90, this angle here, C will reduce. So this angle here, R will reduce. So I can say there, I'll name this R. Inside brackets, you can put 90 minus R. R will reduce. Lesser than C. Lesser than critical angle. If R reduces lesser than C, 90 minus C is greater than, the more this reduces, it's greater than critical angle. Look at the logic. When theta equal 90, R equals C. So 90 minus C, you can get 5119. 5119 is greater than the critical angle. Total internal reflection will take place. Total internal reflection will take place. Now, if I reduce the angle from 90, if theta reduces from 90, R will reduce lesser than C, lesser than the critical angle. Lesser than the critical angle means 90 minus C is more than the critical angle. Therefore, for any angle, therefore, for any theta, total internal reflection occurs. Total internal reflection occurs. Clear? No? That's the logic. So when this is 90, this is C, this is also greater. If this lesser, this is lesser, that is more than the early angle, more than this. More than that means total internal reflection takes place. 90 minus C is greater than, not this, greater than, we can state, greater than, now 90 minus C, we found the value of 5119, greater than 51 degrees 19 minutes. Therefore, for any theta, total internal reflection will take place. Okay, no? So this is your answer for the second one. So logic steps are told. When theta reduces from 90, R is less than critical angle. When R is less than critical angle, 90 minus C is more than 5119. Here 90 minus C, that's more than 5119. The total internal reflection takes place for any angle theta. Okay, for any angle theta. Right? For any angle theta. So it's a very important logic. Huh? This logic explanation is important. Logic explanation is important. Right. Okay. Once you need it, write it down below. Right. Okay. This I have done. Huh? This I have done. Done. Next one, when theta equals 30, when theta equals 30, calculate the angle of refraction on the surface AD and the angle of incidence on the surface AD. I think this I can do it here. This I can do it here. Let's see. Okay. AB, AD. Here, angle of incidence 30. Rarer, denser towards the normal. Rarer, denser towards the normal. This is R. This angle here, it's going to be 90 minus R. Let's apply carefully. Will NA sine 30, 1.6 sine R. Sine 30 is half, 1.6 sine R. Sin R is 1 over 3.2. Sin R is 1 over 3.2. R is equal to sin inverse 1 divided by 3.2. From this you can say R is equal to 18 degrees 13 minutes. In the marking scheme they are given you plus or minus 6. So anything in this range is accepted if you solve it. 18 degree 7 minutes to 18 degree 19 minutes accepted. Accepted. So I'll take 18 degree 13 minutes and work. This angle 90 minus R. 8960 minus 18 degrees 30. 47. 71 degrees 47 minutes. This also plus or minus 6 will come. So plus or minus 6 minutes will come, which means 71 degrees 41 minutes to 71:53 accepted. In that range accepted. Okay. Right. Now, if the space above surface AB is filled with a transparent material, space above AB is filled with a transparent material. Space above AB is filled with a transparent material. There you go. Refractive index 1.7. Calculate the relevant angles for theta equals 30. Right. So theta equals 30. Now we know this. Now you must be careful. This angle is also known, very easy. Now here 1.6 refractive index, 1.7 rarer denser towards the norm. Then you must be careful. So if you do the calculation here, this angle is 18 degree 13 minutes. Okay, no? 18 degree 13 minutes. That angle there, 71 degrees 47 minutes. Now rarer denser, it will go towards the normal. So do the calculation carefully. 1.6 sine 71:47 equals 1.7 sine R1. So this angle here is R1. 1.6 sine 71:47. Sine 71:47. Sine 71:47 divided by 1.7, that is sine R1. From this R1 you can find. If this is R1, this is also R1. Be careful now. If that is also R1, here also R1 here. Okay. This will give you 63 degrees 23 minutes. Plus or minus 6. Huh? Plus or minus 6 minutes. That is 63:17. That is 63 degrees 17 minutes or to 63 degrees 29 minutes. Right. Now, before you conclude, you must find the critical angle here. Critical angle there. Critical angle there. If you carefully draw it, here you go. Here air. You need to calculate this. 1.7 sin C equals NA sin 90. C is equal to sin inverse 101.7. So 101.7 means go back earlier. You have a small idea now. 101.6 is 3841. So if this becomes 1.7, this value will become even lesser. Critical angle is even lesser. Here. Critical angle is even lesser. Right. So now we'll see. Right. So we have drawn. Right. Then draw the ray diagram after calculating relevant values here. So critical angle here, look, critical angle is less than 38 degrees Celsius. Therefore, total internal reflection occurs. So here total internal reflection will occur. The total internal reflection will take place. Right. If the space above the surface is filled with 1.5 refractive index, 1.5 refractive index. Here A, B, D. 1.5 refractive index. Refractive index. This is 1.5. This is 1.6. Find the maximum value for theta. Ray will undergo total internal reflection from AB. Right. So theta maximum here, rarer denser towards the normal. Total internal means goes along the boundary critical angle. Here you go. You can work it backwards. 1.6 sin C, 1.5 sin 90. Sin C is equal to 1.5 divided by 1.6. C is equal to sin inverse 1.5 divided by 1.6. What is your critical angle? Critical angle is 69 degrees 38 minutes. Then what is your angle R? Angle R is 90 minus critical angle. 89:60 minus 69:38. 22, 0. 20 degrees, 22 minutes. If this is 20, then theta m you can find. NA sin theta m 1.6 Sine 20, 22. Sine 20, 22. From this, theta m you can find 33 degrees 50 minutes plus or minus 6 minutes. The correct answer is 33 degrees 50 minutes. 33 degree 50 minutes. Okay. 33 degree 50 minutes. These are basic work. Easily you can calculate if you have done it. Then they are asking you, an optical fiber is made as shown in the figure. Monochromatic light ray enters the fiber from air angle theta, which is slightly less than theta m. If they are asking you not to do, what will happen if theta is larger than theta m? They have to answer this. If theta is larger than theta m, what happens? R is greater than how much? R is greater than 20 degrees 22. If R is larger, this is 90 minus R. 90 minus R. 90 minus R will be lesser than critical angle. 90 minus R will be lesser than critical angle. Therefore, light rays refract into outer medium into 1.5 refractive index medium. Refractive index medium. Okay, no? If the angle is larger, this is less than critical. Less than critical means light rays will refract. That you must write. Okay. Right. An optical fiber is made as shown in the figure. Monochromatic light ray enters the fiber which is slightly less than t time. Less than t time means what? More than t time means refracts. Less than means less means this is lesser. Lesser than 2022. Lesser means this is more than what? More than the critical angle. So total internal reflection takes place. So what are they asking you to draw? Draw the pathway. So here you go. Total internal reflection occurs. Total internal reflection occurs. Total internal reflection occurs. There you go. So these is how the pathway will travel. Huh? These is how the pathway will travel. Okay, no? So inside this medium only it keeps on going. Inside. Yeah. I've shown inside the medium. Right. Okay. So with that, we have concluded week number 2, day 2 paper. Now tomorrow, remember you have week 2, day 3 and a day 4 papers I have given. That also do. So we'll discuss both and finish tomorrow. Okay, no? Right. Okay then. Keep working, be disciplined. Just as you worked in the first week, same intensity, keep going. And this is religiously do and finish it. Okay? So this week 2022 paper is done. Next week we'll be doing 2001 paper. Okay. So as the weeks go on, unknowingly papers are finishing. Okay, no? Right. Okay then. Stay home safe. Catch you tomorrow. Good night.